Hello everyone, I am Bradley Sward, Associate Professor of Computer and Information Science at the College of DuPage in Glen Ellen, Illinois. In this video today, I'm going to look at casting, basically otherwise known as static casting, different types of data. We're just going to use the integer types today, and we're going to look at this from a C++ standpoint, and then also how do we do the same kind of stuff in x86 assembly language. So here is a very complicated chart that's going to get even more complicated as we get moving forward, but it should not really be, none of this should be, earth-shattering here for you today. So characters, shorts, and ints are three basic, at least in C++, three basic data types that we can use to store, variables. A character is 1 byte of storage, a short is 2, and an int is 4. And on my architecture, a long needs to be used to get up to 8 bytes of storage. But if you know how to do these three, or even two of them, you kind of know how they work for all. So what this chart is trying to show is, if I'm going to start with a character and I'm going to cast it, say like, okay, let's turn a character into a short, or turn a character into an int. Or in this case, turn a character into a character. What do I have to do to make this thing work? And I'm going to be very explicit with everything a lot of times, especially in C++. You can be very implicit where you don't have to go ahead and use static casts and things like that. But to get the point across, I really want to make sure I show you that the casting and what happens, what are the good things and what are the bad things as we move from data type to data. So a character to a character is just a straight everyday copy. Like int A, int B, A equals B. I mean, that's all there is to it. I mean, we do that, all the time in pretty much every programming language. And then now character to short, character to int, this is where it gets a little more interesting because you're going from something that's 1 byte of storage up to something that's 2 bytes of storage, or 1 byte to 4. And so this is the lighter green, which, let's see, I guess the green does not match up, but I will make, there we go. So these three here across the board here are just straight up copies, character to character, short to short, int to int. But then these lighter green ones are the ones where you're static casting. You're actually what we call upcasting, where you're going from a smaller data type to a larger one. So you could imagine the reason why this is a light green and not the yellow over here is because anytime I go from a smaller data type to a larger one, nothing will get lost in the process, none of the data, because I'm just basically taking the same data and moving it up into a bigger space, and there's more room for activities and more room for everything else. But now so now on this end, short and int is where you can start to cause trouble when you go from something that's a larger data type into something that's smaller. And as you can imagine, if anything that's in this half over here, once I slam and cut it off, will be lost. So some data will be okay. Anything that can fit inside just this portion of a character won't get lost at all when it gets moved into the character. But anything that takes over this portion, or on the integer side, anything that's over here will get lost as we move down from int to short or short to character. And that's where these three you have to watch out, because, and there's really no way to know if you're going to do this in C++, like there's no way the compiler could ever figure out, especially at compile time, is the value inside that variable going to be something that doesn't get lost. And maybe you've used C#, maybe you've programmed in other languages before, that these sort of things are not allowed. They're allowed, but you have, as the programmer, have to go in and say, I allow you to cast this from one thing to another, especially on the downcasting, because the language nowadays is not going to be responsible for that kind of mistake that could be easily made in C++, because you won't get a compiler warning, you won't get a compiler error. So let me go ahead and show you in a little greater detail here in actual pure C++ what it is I'm talking about, and and everything here in this chart. So I have the 9 different casts here. So I have values for a character, a short, and an int, and I'm going ahead and I'm just taking the character and converting it to char, char to short, char to int, short to char, short to short, short to int to char, int to short, int to int. And so those are the 9 different things from that chart here. And just to show you, that you do have to watch out for these kind of things in some of these cases. In some of these cases, you don't. So, and notice I did not do any casting for A, from char to char, short to short, or int to int. Again, because there's no need to do that. You could, but you're just wasting your time if you're taking all, the clock cycles to turn an int into an int. Nothing has to occur, but more has to be done to upcast for sure, and then possibly downcast as well. So let me run this with these values, 81, 113, and 50. And these numbers come out fine. And let me just show the Q comes out because C++ prints characters as ASCII characters. So I should use a static cast, but I just want to use the C style just not to confuse things, just to get the point across here. Is that when I run this again, you can see 81. Whenever I take in this guy, 81, and I try to upcast it from character short and character to int, everything's fine. Same goes for short to character, and short to character, short to short, short to int. Downcasting works because the value, coming back again, the value inside of here in the short fits inside the same space of character, and the same with int here. That it only fits in this one, or that fits in this 2 bite-sized part of the value, so that if I slam this thing off, none of the data gets lost. So basically all the data is stored in here, and then so that once it gets hacked either here or there, it doesn't get lost at all. And so you can see that. And then for int, it's the same deal. Int to character, int to short, int to int. They all do their job. They're all doing what they're supposed to be. Okay, so then now that shows you how casting works, at least at the C++ level. And now this chart is about to get a little bit more interesting, because now how do we do the same kind of things when we don't have the glory of the C++ language to do all this for us? We have to do this manually in x86 assembly language. And here is the chart. Okay, so here is the chart again. The names have changed, but kind of everything else is staying the same. A character in C++ is a byte in x86. A short is a word, and an int is a double word. And so we're doing the same stuff, but instead of character, short, and int, I'm just replacing this. This is byte of storage. This is a word of storage. This is a D word of storage. Everything on my system is running in little endian order. And that makes it a little easier to work with the kind of details we're talking about here. So again, if I move from character to character, the same data type in assembly language here, I'll just use a plain old move. Just anything. That's easy, because it's a straight up copy with the same size data types. But as I move from character to short, character to int, it gets more interesting, because I can't use a simple move, because mainly because it doesn't know if I'm using a signed value or an unsigned value when it comes to what's being stored in that character, and so that everything gets transferred over correctly. And so part of the deal here is I have to either do move 0 extension or move sign extension, so that I go from the smaller space to the larger space and keep that integrity. Because if I put 120 or 255 in here, and I just moved it as a signed versus unsigned value, I'm going to get a different result when I use these things. If I just use a straight up move, you might not get what you're expecting. So it's coming back again. So byte to byte, move, byte to word, you have to use one of the fancy 5-letter extension operations, and same goes for byte to double word. And so word to word is a straight up copy. And the same thing goes whenever I'm going to my cell, the same size, it's just a plain old move, and you don't have to think. When you're moving to upscaling here, upcasting, you have to worry about the sign. You have to use either move sign extension or move 0 extension. And down here, when I'm downcasting, the same kind of rules apply. You have to watch out that, one way or another, that you're not losing data as you go from a larger data type to a smaller one. And so you can do a straight up move. It's a little more complicated when you're using memory, but if these are just registers and things like that, it's a lot easier to use those kind of deals. And so, but you still have to worry, and you still have to watch out that when you go from, when you're moving from a short to a character, and I'm just using a move, and I'm just moving, the AL portion of the EAX register, that that I'm not losing anything. Okay, so let's take a look at this in x86 assembly language. Oh, I just noticed it's late. You can that if just to show you the proof of that, if I I did all this and I forgot all about this. If I change the values of A, B, and C to large values, and then especially on the downcasting side, you will see that you will be in for a world of hurt here. Let me just run this here. Now you can see here that again, all the characters work fine because I can only go into larger spaces. And anytime I'm going into a space that's my sized or larger, you can see 3 things are that way, 2 things are that way, 1 thing one way. And then you can see as I go to downcast from short to character that there's no way it can store that data, so it's doing its best. That's the best it can do. And when I do 2 billion here, and I convert that down into a character, it comes out as 0. I guess the first 8 bits of 2 billion appear to be 0, just the way it goes. So just to show you there before we move on to the actual x86 assembly. All right, so let's go through the 9 different ways to do this in assembly language. So we'll start here, byte to byte, very simple. So BBB is my byte, and I'm in just a simple move operation. I'm going to move a byte into a byte. So I can use move, I can say AL comma BBB. And just for this, say if I don't clear out the entire EAX register here, let me show you here. I will go ahead and call dump reg. And I will run this, and you will see that you look at this, like the EAX register is the only thing I care about here, and you notice it's this, oh my goodness, it's got an awful number, and you see 13, and remember this is all in hex, so 13 in hex is 19, so the low end, the AL portion of this got copied correctly, but everything else kind of is basically still there. That's AL, so there's AH, and there's all the rest of the EAX register. So if I wanted to, if I called it call write int in this situation right here, I'm going to get some just garbage number. I get 170 million or whatever this is, 1.7 million. It's not the 19 I'm supposed to be getting. So for something like this, because of the way this works, you either have to put a 0, at least in this case, into EAX, and then you'll get the 19 that comes out. And this will print out in decimal format. There's my plus 19. Or the other way, even though it says it's just a straight up move, just to prove this works when you call, when you go to call the write int on this, I do have to say move sign extension into the entire EAX register. So I can do that this way as well, and there's my plus 19 there. But you don't normally need to do this kind of stuff unless you're calling write int. If I'm just going ahead and saying I'm just copying over, and this is all I want to do, I would just say something like this, copy AL comma BB, and then I can do whatever I want to do with that value. That just shows you to get, what we have to jump through in order to supply the write int function, the parameter that it needs. It needs the entire EAX register filled so it prints correctly, because it's going to print whatever's in the full EAX register no matter what. Okay, so then moving on up, I can't just go ahead and say move BBB into the AX register, because BBB is a byte size element, AX is a register that is a word size. So if I go to build this and bring it up here, instruction operands must be the same size, and that's where again the move sign, move 0. In this case, these are unsigned, so because I don't have the S in front of it, I just kind of neglected to do that. In this case, then, as long as I know that, I would do a move 0 extension. Or if this was a signed byte, I would have to do moved sign extension if I wanted to put a negative in there or something like that. That's just how things work. But I'm trying to keep it simple, and I know it's getting a little complicated as I'm talking here for the most part. And so now with the move sign extension, and that's the only, I don't think there's any 6-letter, maybe there are, but I haven't counted them in my travels here in assembly language, that I could say, okay, move BBB into AX and then call write int. And let me just, for the sake of this, just show you, let me just move 0 into EAX. just to show you how things work out. And now things compile, things run, and I'm right back to getting my plus 19, my positive 19 out of the call write int function. And the same would apply if I wanted to move this thing into the entire EAX register. Now I don't need that move anymore because I'm taking BBB, which is a byte, and I'm extending it out, and it's going to be just 0, 0, 0, 0, 0, 0, 0, 0, 0, and then eventually 1, 0, 0, 1, 1 for 19. Binary. And there's my plus 19 it prints out. So that's how you handle, that's how the bytes would get handled. So let's talk now about how the words would get handled. It's more of the same, but again, now we have to watch out when we work our way backward. Okay, I'm going to start with the easy one, the plain old move. And for that one, then I'm just going to leave the EAX register 0. So I'm going to move whatever's in CCC, which is a word, I'm going to move that into the AX register, because that's the only straight up move operation that works. And I can call write int again here, and this will print out 42, my plus 42. And again, that's because whatever's in CCC is a word, it's getting copied into a word, and then because I already blew out all the extra stuff just to make it easy on ourselves, then it'll write the integer correctly. And so again, moving this thing up, this basically just gets eliminated when I do this. Saying take CCC and move, but again, I can't just do a straight up move. I'm going to get that operands are not the same size, and so I'm going to have to do the move 0 extension to make this thing work. But in this case, I don't have to do anything more because the entire EAX register is going to get blown out when up by the 42 that's in here. There's my 42. And again, this is a problem working backwards. Instead of doing something like this, I can't do a move 0 extension, but I can do a move CCC to AL. And it goes, and again, it is, this is one of those things I didn't want to say until it happens here, but like this does not work because CCC is a word, AL is a byte, or I'm sorry, is a byte size register, and you go, well, how do I do this on the back end? And this is where you have to use the byte pointer, word pointer, dword pointer to make this thing work, because otherwise the assembler doesn't have a clue what it's supposed to do with the memory. So CCC is a word, and everything is stored in little endian order, so everything works out like this. If I just say, take this, go to the memory address that CCC is, and there's a word stored there, but pretend like it was a byte, and send that information into the AL register. And when I do this, now I'm going to have to put back EAX so this gets stored right, and the 42 again will come back and it's magically there. And that is because, again, this CCC is the memory in here is being stored word, and all the little endian stuff is being stored here in this byte. So when I go, okay, go to CCC, and this is the memory location, and take this, treat it like a byte, copy all the data in here, everybody's happy with the way it turns out. But then if I just change this to like the number 342 or something like that, you will see I get a plus 86 out of that, because this is where I'm saying you have to watch out for this, is because I'm taking a number that's larger than 8 bits of storage and just trying to jam it in, and it just won't work. There's just no way it's going to work, and you lose data pushing your way back. But now, so this is a move, but then this is a move with a pointer operator that basically, and it's a cast. You're casting something from a larger data type to a smaller data type, and this is just the syntax to make it work. So now, just to finish up, you can see here that it's more of the same here when I go with doing something like this. I can just do a straight up move. For int, I can just say move DDD into the EAX register and call write int, and it'll print the 102 just fine. There's the plus 102 because DDD is a D word, EAX is a D word, and this write int function just wants the EAX register blown out, so it's happy. Everybody's happy there. But now, coming back again, to make this work, if I want to turn this into AX, or I want to turn this into AL, I have to use the byte pointer things, because otherwise the assembler thinks it's a double word. And you have to go out of your way to say, oh, I'm smarter than the compiler, I'm smarter than the assembler. I want to take DDD, and I want it, which is a D word, but I want you to treat it like a word. And now it'll fix that one, because now instead of this being a 32-bit register or value. Now it's a 16-bit value, and now 16 to 16 matches up. And the same works here, where I can say take my byte pointer and do the same. And again, you say like this comes out all weird, and that's again because I did not zero out the EAX register here to keep it simple. That simplifies it. That makes it work a little bit. Yep, it actually does work in this case. Okay, so plus 102 plus 102, and so everybody's happy here. And but again, if I make this a large number, 2 billion. This number is, it uses pretty much all the bits stored of 32 bits. There's no way this number can translate when you cut it down in half. There's just no way. And 2 billion comes to that number, 37,000. Let me see about this here. Let me see if I have to zero it out each time to get it to be what I presume. Yes, I needed to do that the whole time. So because I put these in reverse order of what I was intending to do. So yes, 2 billion as a double word, when you crank it down into a word size element, it stores as 37,888. That's all you can do with it. And if you bring it down and crank that thing into a byte, basically all you get is 0, which means basically the first 8 bits of this number, 2 billion, are zeros as it gets condensed down into bytes. So this is not an easy demonstration for a lot of people. It takes a lot of thinking. We almost never think at this low level, especially as students. It's hard to imagine, because we're basically one or two steps away from how the computer is actually doing the actual work on the CPU. And when it comes down to reading the hardware and the gates and all that kind of stuff, that we're almost there. I mean, we take this so for granted. The higher the level, the language, the more we do take it for granted. But at the lowest levels, this is what's going on. Our high-level language is being converted into these kind of moves and these kind of extensions and so forth and so on. A lot of times it's using, I just used the registers for an easy example. But coming back and using variables for everything. We will hit this near the last 2 weeks of the term, where for some people it says it simplifies everything, but other people say it just makes things more complicated when we set everything up properly using local variables for parameters and for local variables and things like that versus globals, because these are all set up as globals. And that's not how programming works in 2021 or even 2011 or way back. Like it's a newer thing, but it is not new by any stretch of the imagination what the compiler has to do when we neglect data types and we waste clock cycles. So when we do this as well, if we try our best to make sure that the CPU doesn't have to convert data types, because you can see here it takes processing to make these things work. Things we're not intending to do. Or a move with a word pointer is going to take more work than just a move with something like that. Maybe it is, maybe it isn't. I don't want to get hit by people that say that's technically wrong. But I'm just saying that some of these move operations do take slightly longer to resolve than others, and something like this is probably faster than something like this. So that's all I wanted to say there. So as always, thanks for sticking it out with me. If you have any questions, if I'm unclear, it's almost 1 in the morning here where I am, just drop me a line here at swardb@cod.edu or here on YouTube, and I'll answer them and correct the error if I made one. Nothing intentional as always here. So thanks as always, guys, and have a good day, and I'll see you next time.